Okay, in this video, we're going to talk about how to use the precise definition of a limit to prove that a sequence converges to a certain number here. Now that should sound kind of familiar. You did, if you took 21A here at UC Davis, you may have done something similar with a precise definition. So that's what's going on here. So the sequence would be a sub n equals 3n over n plus 2. I wrote out some of the terms here, and we know that to decide if it converges or diverges, we would take the limit of that sequence. And we know either using L'Hopital's rule or looking at the powers and noticing that the powers are the same, that this limit's just going to be 3 over 1. Okay, so the limit is 3. Now to prove that, if you get asked to use the precise definition of a limit to prove it, here's the idea behind that. Okay, the limit is 3 here, and you can think of a sequence as just a bunch of dots, right? A sub 1 is 3 over 3, which is 1. A sub 2 is 6 over 4, 1.5, 9/5. Okay, and what should happen if this sequence really converges to 3, these dots will get successively closer to my limit of 3. The idea behind the proof then is this. If the limit is 3 and we choose some distance away from the limit, which we call epsilon, that should sound familiar from 21A. So in this case, I'm letting epsilon be 1. So if I'm 1 unit away in either direction from my limit of 3, there should be some n value, right? Number of my term of my sequence, for which if my n is bigger than this number, all of my successive sequence values are even closer than 1 unit from my limit. Okay, so one way to visualize this, if you draw like horizontal lines corresponding to whatever epsilon is, that first dot that hits and crosses this line, and every dot after that is within the 2 green lines, that's what we're looking for. We're looking for that magic n number, and we're going to call that specific n value capital N. Okay, so more specifically then, what we just showed here was if epsilon was equal to 1, if little n, my sequence values, are bigger than n equals 4, okay, and remember this terminology, the absolute value of a sub n minus L will be less than epsilon. That's just saying the difference between your sequence value and the limit, right? This is a difference. That distance is going to be less than epsilon. Now, the idea behind the proof is to not find out what n is when epsilon is equal to 1, but to find out what n would be for any epsilon, no matter what epsilon is. So we're going to find n in terms of epsilon, so that for any epsilon greater than 0, if n is greater than, okay, I've already worked out the answer, but we'll be looking for some number here, some value in terms of epsilon, for which the absolute value of a sub n minus L is less than epsilon. So to get this value, we're going to just plug in. My value for a sub n is 3n over n plus 2. That's my sequence. Minus my limit, which is 3, less than epsilon. All I did from here to here was do a common denominator. Okay, you guys can do that. I know you can multiply top and bottom by n plus 2, distribute the 3. We'll be left with the absolute value of negative 6 over n plus 2. With absolute values, you can break them apart. This is equal to the absolute value of negative 6 over the absolute value of n plus 2. Of course, the absolute value of negative 6 is just 6. And okay, remember with sequences, n starts at 1, then 2, then 3. So we know n is a positive number, which means n plus 2 is always going to be positive as well. So we can just ditch the absolute value, okay, on the bottom. Then, if you manipulate this, if you take the reciprocal and split it up and solve for n, you get n is greater than 6 over epsilon minus 2. And that's what we will call capital N. Okay, so that's how I found this value here. And just to check it, you can see, remember in my opening example, we had epsilon equal 1. And if you plug in 1 there, notice you end up getting 4, which is what we saw from our picture. But now, no matter what epsilon is, if epsilon's 1/2, you can figure out what n needs to be. That means you need to go to your 11th term in your sequence before your sequence values fall within 1/2 of the limit, which is 3. And if epsilon is 1/100, that's really, really close. You would have to go out 599 terms for your sequence values to be within 1/100th of the limit. So that's a review for the precise definition of the limit. You may or may not see this in class. Some professors choose to teach it, some ignore it, but just in case you have that there. In the next video, I'm going to show you another way that we can prove a sequence converges. That's not using the precise definition, but using a different strategy.